So the next topic we want to discuss is about primitive roots. Mod n. So first of all, we already know for what n does the primitive root exist. Then you find primitive root mod p, and then lift it to primitive roots mod p to the power alpha. Okay. So this is about primitive root computation, computing the primitive roots. Now, so counting, then we have to count. So suppose, so how many solutions exist mod p to x to the power d congruent to 1 mod p, for example. Yeah, this is a meaningful thing to have, right? So how many solutions exist? So first of all, computing orders. Mod n, right? So now there are various theorems which help you computing more order mod n. Then finding reduced residue class. And use it to prove theorems, all right? And prove interesting results. For example, can you tell me if I add all the, or if I multiply all the residue classes, what do I get? What is product of all r to the I, where I mod n, where I is between 1 to n, and I and n is 1. Okay, so these kind of results, right? Now, using various results on what is the order of a to the u mod n, yeah, what is the connection between this guy and using this to find out the order of various arguments. Then how many primitive computing number of primitive roots modulo n, how many of them are incongruent. Then asking questions like these, x to the d congruent to 1 mod p. Yeah, so for this, recall, you had this theorem that x to the d minus 1 congruent to 0 has exactly d incongruent roots. If d divides p minus 1. Yeah, all right. So this is what we did in the primitive root business. Then we talked about multiplicative functions, right? So multiplicative functions. So in multiplicative functions, we discussed about Euler phi function and the properties of Euler phi functions and properties. Compute Euler phi function of few and few numbers, then finding Euler phi inverse. So like, for example, we have done this, and find n such that p of n equals to 6, for example. Second, we discussed about tau function. We talked about sigma function. We talked about number of divisors functions, right? So we talked about a bunch of multiplicative functions. So multiplicative functions. Their properties, and more importantly, the Mobius inversion. Right? So connecting different functions with the other using Mobius inversion. All right? Or proving certain properties. So proving properties of multiplicative function. Proving properties of multiplicative functions, and what you do is the following: you prove it for prime power. Then okay, so then what are the other things we have discussed? We discussed about we discussed in length about pseudoprimes. Like showing some number is a pseudoprime mod whatever mod n. Yeah, so showing some number is a pseudoprime mod n. All right, so here another issue is, so we talked about quadratic residues and primitive roots. So there are some showing that certain things are primitive root. So showing or finding, say for example, connection, one interesting problem could be find primitive roots, or show that numbers of certain type, say -1, I think 5 is -5 is primitive, is not primitive root modulo some prime p based on structure of p, right? So similarly, there are certain structures of certain numbers which will not be primitive roots. Another interesting problem here was, we already saw in our assignment, we saw, okay, I'm going back and forth as I remember. So we saw 3 by p. What about 6 by p? Yeah. Or what about, 5 by p? Yeah. Can we come up with formulas for these guys? Okay. Again, the idea is to be able to use what we did for 3 by p. All right. The pattern is exactly the same as 3 by p. Yeah, you are following the same thing to get for 6 by p. For example, 6 by p is better because 6 by p you can break it down to 2 by p and then 3 by p, and then again apply the same kind of argument. Here you don't even need to apply the Chinese remainder theorem, and similar things can be done here, right? You apply first, you apply the you see if p is congruent to, so you just invert it by, this will become 5, this will become what, p by 5, and then you apply and see. P by 5 will depend, the value of that will depend on what your p is mod, what your p is, right, mod 5, so on and so forth. So these kind of properties. Then coming back to pseudoprimes. So the things we discussed in pseudoprimes are definitions. So and then we had Carmichael numbers. Right, showing something is a Carmichael number. Finding pseudoprimes, show that there are infinitely many. So we have already shown this, show that there are infinitely many pseudoprimes. These pseudoprimes. Base 2. Yeah. So what about base 3? So that's one thing you can look at. Then we had a bunch of factorization problems. So factorization. In factorization, we have only studied namely pharma and trial and error, right? Then going back to, so then we can discuss about solving polynomial congruences. Solving polynomial congruences and applying Hensel's lemma. Okay. Yeah, and then system of linear congruences. No, you will have to, so both, you will ask, you could be asked problems to, you could be asked to apply Hensel's lemma. All right. Yeah. Yeah. Okay. Yeah. The idea is not to have a, okay, let me just. System of linear congruences. So solving system of linear congruences. Then basically linear congruences, then solving linear congruences. Particularly you were interested when, so one interest could be like, remember the stamp and the stamp problem, and the you want to buy two different things and you have certain amount of money, how many different combinations of those you can buy. Yeah? So the problems where you need positive solutions. For example, then you have solving linear Diophantine equation, which is same as linear Diophantine equation. So linear Diophantine equations, essentially, which is solving congruences, right? Linear congruences. Then you have continued fractions. So you could be asked, for example, remember we had this problem where either you could be asked to find certain quadratic equation, have certain nice linear congruences, right? Or solve using algorithm. Yeah, for irrationals. Well, or solve using Euclidean algorithm. for rationals. Then we have GCD and yeah, divisibility. Yeah, so these are the kind of things we have really. Now there are certain things you should know is which I haven't said here is the Chinese remainder theorem, right? So unifying Chinese remainder theorem with, so think about it, Chinese remainder theorem is kind of a connecting link between a lot of things. Yeah, it connects when you are doing Mobius inversion for, sorry, when you're finding consecutive numbers which are basically so you had a problem where you wanted to find out three consecutive numbers such that Mobius evaluates to 0 on them. You had to use Chinese remainder formula or Chinese remainder theorem to find out exactly what those numbers were, right? Similarly, if you remember, if you recall, you had to do, if you look at the assignment, if you look at the assignment you did, which was 3 by p is 1 if p is congruent to 1 uh, 1 mod 12 or 11 mod 12 and minus 1 if p is congruent to 5 or 7 mod 12. Now to even prove this, you had to use Chinese remainder theorem. So there are Chinese remainder theorem is kind of a connecting link between a lot of things. Similarly, you have Euler's theorem. It's also connecting link between, sorry, extended Euclidean algorithm, sorry. That is also a connecting link between a lot of things, right? So you will need to use these tools over and around. So RSA, right? So RSA tests. So basically properties around RSA, right? Trying to, yeah, so properties of RSA, right? Like why you don't need P and Q exponents to be near. Things like that. P and Q to be not too close.